In this video, the first question we would like to answer is the question, what is an unusual event? An unusual event is an event that has a low likelihood or probability of occurring. It is almost similar to a rare event, an event that doesn't occur all the time, but still has a chance of occurring. So, another way to say or define an unusual event is an event that is not likely to occur as often as other possible outcomes in the sample space. As a rule of thumb in statistics, we usually ask, what is that cutoff threshold that is most commonly used to typify an unusual event away from an event that occurs more often? Typically, an event with a probability less than 0.5 or 5% is considered unusual. As I said earlier, this is a mere rule of thumb. In actual research, the context of the problem usually helps to define what probability cutoff value should be used as a as a way to demarcate or distinguish between unusual events and usual events. So, for this class, we would set up the value of 0.05 as that cutoff. So if the probability of an event is lesser than 0.05, we will consider it an unusual event. But remember, this is a mere rule of thumb, not the same in actual practice all the time. So we take an example. The data in the table below represents the results of a survey in which 200 people were asked their means of travel to work. We have drive alone, carpool, public transportation, walk, other means, or even work at home. And of the 200 people surveyed, the frequency of those who responded to each of the different means of travel were provided here in this table. For example, 153 people drive alone to work. So, based on this frequency, we can compute the probability that a person would drive alone to work. That probability would be of the total frequency, which is 200, it will be, we stand a 153 chance out of 200 of selecting someone who drives alone to work. And that will be equal to 0.765. And for those who carpool, 22 out of 200, this is 0.11. For those who go by public transportation, that will be 10 out of 200, 0.05. For those who walk, that will be 5 out of 200, and that will be 0.025. And then 3 out of 200 for those who go through other means, that will be 0.015. And for those who work at home, we have 7 out of 200, which is equal to 0.035. Now, based on this probability model, where you have the possible outcomes along with the respective probabilities, we want to use the survey data to build a probability model for the means of travel to work. That is what we have just done. We have documented the possible outcomes and their respective probabilities. That is completed in part A. Check. Then for B, estimate the probability that a randomly selected individual carpools to work. Interpret this result. Well, for carpool, let us see. For carpool, we have these cells here. And so the correct answer to that question for the probability that a person carpools to work, probability of carpool, that will be equal to 0.11. So the interpretation of this will be as follows. To begin the interpretation, I would note that 0.11 is the same as 11%, or 11 out of 100. So I would say that a fitting everyday interpretation would be that if 100 people were randomly selected, that is out of 100, we would expect 0.11 which times 100, which is 11 people, to travel to work by carpooling. That is based on the results of this probability. The next part of the question said, would it be unusual to randomly select an individual who walks to work? First of all, step one will be, what is the probability that a person walks? And looking at the table, that will be 0.025. The next step, after computing the probability of that event, is to check if that probability of work is less than 0.05. If it is a yes, then it is unusual. If it is no, it is not so unusual. So in this case, what is the probability of work? It is 0.025. Well, as you can observe, 0 matches 0, 0 matches 0, 2 is less than 5. So the probability of work is definitely less than 0.05. So that's a yes. That makes this event an unusual event. Again, as a caution, the probability of 0.05 should not always be used in practice or in research. So, for the purpose of classroom illustration, we have adopted the threshold of 0.05. Having learned about unusual events, we proceed to learn about methods of assigning or computing probabilities. There are three methods: the classical probability assessment method, the relative frequency assessment method, and the subjective probability assessment method. Let's take them one after the other. We start with the classical probability assessment method. You see, the method of determining probability based on the frequency or count of the number of ways an event or an outcome of interest can occur compared to the total number of ways any outcome or event can occur when the individual outcomes are equally likely. Keyword, equally likely. This is called the classical probability assessment method. So, in a nutshell, it considers possible equally likely outcomes. So if the outcomes are equally likely, for example, if you toss a die, each of the faces of that fair die would be equally likely. And if I ask, for example, what is the probability of a 6? Then you count the number of ways a 6 can occur, which is 1, since it's only filling one face of the die. Out of the number of possible outcomes, there are 6 possible outcomes. So each face of a die stands a 1 out of 6 chance of occurring. And take note, that is based on the reality that all faces of the fair die are equally likely. Then we proceed to the relative frequency assessment method. So this is the method that defines probability as the number of times an event can occur divided by the total number of times an experiment is performed in a large number of trials. This in particular has to do with computations based on past data collected. So it is actually a practice, something that has been done repeatedly, and you have collected the data, and then you're using the frequency at which a particular event occurs compared to how many times the experiment was tried to compute the probability of that event. We'll see some examples later. Then, for the subjective probability assessment method, it is the method that defines probability of an event as reflecting a decision maker's state of mind regarding the likelihood that that particular event will occur. A quick example is if a financial reporter asks what an economist about the likelihood that the economy will fall into recession in the next year, the views expressed by this economist would be very, very subjective. And so that would be whatever value is given as a probability value here would be arrived at using the subjective probability assessment method. So, a very important note, the empirical method, also called the, um, the relative frequency assessment method, obtains an approximate empirical probability of an event by actually conducting a probability experiment. Whereas, on the other hand, the classical method of computing probability does not require that you actually perform the experiment. Rather, it relies on counting techniques and also requires equally likely outcomes. This note concerns the two methods that have formulas attached to them. So with that said, let's proceed to an example. In this example, we would like to determine whether the probabilities below are computed using the classical method, the empirical method, or the subjective method. We have points A, B, C, D here. Before proceeding to answer these questions, a quick reminder. For the classical method, you do not necessarily have to carry out the experiment to compute the probability. You only need to consider the possible equally likely outcomes. Then, for the empirical method, also called the relative frequency method, you actually use collected data in order to do that. Whereas the subjective method is purely based on expert or decision makers' thoughts. So for question A, the probability of having 7 girls in a seven child family is 0.00782125. To compute this probability, we do not necessarily have to have um, this occur where you have exactly 7 girls in a particular family to compute this probability. No, we don't need to do that actually exactly, but we can consider the possibility of all the possible outcomes. And in this case, this would be computed using the classical method, using counting techniques and knowing that the possibility of 7 girls in a 7-child family is also likely. Question B. On the basis of a survey of 1,000 families with 7 children, the probability of a family having 7 girls is 0.0059. Well, this is based on a survey of families with 7 children. So this is actually based on collected data. So this will be arrived at using the empirical or relative frequency approach. For question C, according to a sports analyst, the probability that a football team will win the next game is 0.45. I bet this is obtained using the subjective approach. Then on the basis of clinical trials, the probability of efficacy of a new drug is 0.83. Take note here that this says on the basis of clinical trials, which means this has to do with data already collected during initial trials. So this probability would have been computed using the empirical method or relative frequency method. With that done, we proceed to the next example. In this example, we are told that in a national survey, college students were asked, how often do you wear a seatbelt when riding in a car driven by someone else? The response frequencies appear in the table to the right. Never, rarely, sometimes, most of the time, and always. We have to construct a probability model for a seatbelt used by a passenger. The first step would be to compute the total frequency by adding up all of these numbers and then to create a new column of the respective probabilities. We'll do that now. To begin with, the sum of the frequency is 4748. So for the respective probabilities, we're considering 141 divided by 4748. That will be put right here. 141 divided by 4748 is 0.0297. 330 divided by the total is 0.0695. 534 divided by 4748 is 0.1125, and the rest 0.2624 and 0.5259. So here we have the required probability model, the different outcomes and their respective probabilities. Now, the next question says, would you consider it unusual? Remember, unusual would mean the probability is less than 0.05 for the purpose of this class, but it is not always so in practice. So back to the question, would you consider it unusual to find a college student who never wears a seatbelt when riding in a car driven by someone else? We look at the outcome, never wears a seatbelt. So that would be the first entry here. So we have never. The probability was 0.0297. So step one, as usual, compute the probability of never, which we already have in the probability model. It is 0.0297. Step two, you compare. Since the probability of never is less than 0.05, we would consider it what? Unusual. It is unusual to see a college student who never wears a seatbelt when riding in a car driven by someone else based on the data collected in this national survey. We now proceed to the next example. In the next example, we're told that Marco, John, Clarice, and Roberto work for a publishing company. The company wants to send 2 employees to a statistics conference. To be fair, the company decides that the 2 individuals who get to attend will have their names randomly drawn from a hat. Question A. Determine the sample space of the experiment. That is, list all possible simple random samples of size n equals to 2. So since they want to select 2 persons, let's say for the first person, this is the first person. This person could be Marco, M, John, J, Clarice, C, and Roberto, which is R. But that would be for just the first person. Well, if Marco was selected, it could be followed by, what do you think? Do we still have Marco, John, Clarice, and Roberto? The reality is, Marco cannot be selected twice. So we take that out. Then it means that if John was selected first, it could be followed by the remaining 3, which will be Marco, C, and R. And then for C could be followed by M, J, and R. And then R could be followed by either M, J, or C. Now we need to look more closely. When we have MJ, that will be M and J. This is the same thing as JM. That is, Marco and John is the same thing as John and Marco. So we don't need to repeat that. So I'm going to delete this. Then if we have Marco and Clarice, That is the same thing as Clarice and John and Marco. So I'm going to adjust that too. So if we remove all the repetitions, this is a cleaner version. So the sample space will be either Marco and John, Marco and Clarice, Marco and Roberto. It could also be John and Clarice, John and Roberto, and lastly, it could be Clarice and Roberto. So there are 6 possibilities here. What is the probability that Clarice and Roberto attend the conference? So this will be probability of C and R, which is the same thing as RC. So that will be equal to the probability of Clarice and Roberto attending the conference would only claim 1 point out of 6. So this is 1 divided by 6, 0.166667, which can be rounded off to 0.2 if taken to 1 decimal place. Then, what is the probability that Clarice attends the conference? In this case, that would consider the following possibilities. All outcomes that involves Clarice. So let us see. That will be 1, 2, and 3. So that will be 3 out of 6. So probability that Clarice attends, that will be 3 out of 6 based on what we see here. Then what is the probability that Roberto stays home? Well, probability that Roberto stays home, that R stays home, means Roberto is not going. So let's see, in what instances do we have Roberto not going? What I will do will be to look back at the sample space and consider cases where I don't have R. That'll be 1, 2, 3. So there are only 3 instances where Roberto is staying home. So that will be again 3 out of 6, same as 0.5 and same as 0.5 up here. Take note, these 2 events will be said to be equally likely since they have the same probability.